Hi, BC friends. Like Miss Yam said, it was a little bit different when I have a bit of a bigger audience. I'll still try to be my normal self. And since she promised, that I'd be entertaining, I thought obviously I would start with, this lovely image. I know you all probably browse the math jokes subreddit, so maybe you find this funny. It's not really all that funny, but there we go. You can see I was Googling polar coordinate jokes. So anyway, I'm going to talk briefly about Limacons with an inner loop. So Miss Yam, in her previous video, covered Limacons with a dimple, and now we're going to cover Limacons with an inner loop. And I think the key to sort of think about here is that if we think about the general form here, where we look at r equals a plus or minus some b times a trig function, whether that's sine or cosine here, right? We're just going to have symmetry, and it's sort of going to be facing a different way, depending on what trig function we have there. When Miss Yam was looking at these things, A was bigger than B, the absolute value of A, that is. The absolute value of A was bigger than B. And today, we want to think about what happens if B is bigger than A, the absolute value again, right? So what happens if this B here is sort of relatively large compared to A? And I tend to think about polar slightly differently. I know that might scare some of you. I like to think of it sort of with a T-chart, and also thinking about the graph in our normal Cartesian world, right? So I have I'm going to think today about graphing r equals 1 plus 2 sine theta. That's what we're going to start with. And I've used Desmos here, and I've graphed y equals 1 plus 2 sine x over here on the left, this guy right here, right? That's just what that graph looks like. Maybe you did that in a TFA or a TIC class. I know my sections certainly, would feel very, very comfortable graphing that, right, guys? So this is what that looks like, and that's going to sort of help me translate this down below to a polar coordinate graph. So I've also made a bit of a weird T-chart here, and we'll talk about why I chose these particular values. You guys could have easily punched these into a calculator, or used your knowledge of the unit circle. I wanted these in decimal form somewhat, so that I could be able to talk about them, and approximate them on the polar coordinate graph. So I'm not using, root 3s and root 2s. I'm using decimals here, but, you certainly recognize some familiar looking things, right? The 4-1 there from root 2. So anyway, let's talk briefly about this function up here, this guy, 1 plus 2 sine x. And let's think just very briefly about the fact that we haven't changed the period. The period is still 2 pi, okay? And that's sort of going to hold still, hold constant for these types of graphs for what we're going to study here. That the period is going to be 2 pi, and we're going to need to consider all the values from 0 to 2 pi in order to graph things. Okay, there's still going to be some symmetry here with sine x. Thinking about, whether that's symmetrical about the x-axis or the y-axis, you should be able to sort of piece that together in your minds based on what you've already seen. So let's see why we picked these particular values, and let's dive in. Okay, so we haven't changed the period, and we see that our graph is sort of centered around 1, right? Right, if I draw the line y equals 1, it's sort of centered around that. And that's going to be important because when the absolute value of A was bigger than the absolute value of B, we didn't dip below that axis, the x-axis. But because B is bigger than A relatively, we're going to dip below the x-axis, and that's sort of where we're going to run into some problems. So let's just try to graph some points here. Okay, and let's see maybe if we can understand where this is going. So I'm going to graph just the left side of my t-chart here, this left guy, and let's plot some points here. So I'm going to use some different colors to sort of help illustrate things. Okay, so I'm going to mark this point here in red, and maybe this point up here in green at sort of the apex. Okay, so let's draw that red point. So when theta is 0, right, along this axis, we'll say this guy out here is 1. So there's my 0, 1, right? And when theta is pi over 2, so up here we're out at 3. So maybe if this is 1, I don't know, maybe this is 2 and this is 3 out here. Maybe that's 3. Okay, so we have these things, and now let's think about what is happening in between. At pi over 6, I'll just use black for these points because they're sort of in between and kind of boring. Pi over 6, we're out at 2, so maybe that's out here, not super far away. Pi over 4, we're only a little bit farther, so maybe like here. And pi over 3, here we're just a little bit farther out, so maybe out here. And if we think about what the curve is doing, what this curve is doing in this region right here, right? Let's just think about this sort of sinusoidal curve between 0 and pi over 2. It is increasing fastest at values close to 0, and it sort of slows down out closer to pi over 2, right? So r, if we think about this, right? Again, y equals 1 plus 2 sine x. That's the same as r equals 1 plus 2 sine theta, right? We really could just call this the r axis, and this the theta axis. R is increasing faster at the beginning, and then sort of slower at the end, right? So if we were to piece that together, and I were to draw this blue piece in here, it would look something with a rough sketch like this. Sound effects not included. It's going to look something like this, you know, not perfect, but that's not terrible. Not terrible. So it's going to look something like that. And now let's think about what would happen coming down from that. I don't know. Maybe we'll find a fun color. Maybe this guy. We'll use purple. I don't know why I would ever pick purple. Coming down from there, let's talk about what happens sort of on the exact opposite. I didn't include that in a t-chart. You could make that t-chart right next to this one in your notes if you wanted to, right next to this guy here, and you would see, right, there's going to be symmetry there. As I come down from pi over 2 to pi, I'm sort of thinking about the second quadrant of my graph, right? If we think about, you know, here being the first quadrant and here being the second quadrant, we don't really think about that with polar coordinates so much, but we could think about this guy. I'm going to have the exact same sort of symmetry, and we would end up, I'm going to use red again for this point, red again for these guys, at pi and 1, right? So right here, and I would have some symmetry. So again, if I use my purple, I would have some symmetry here. I'm going to be very bad at drawing this without some markers in the middle, but we can see that we'd have symmetry here. That's not so bad. That's actually really not so bad. And again, because this is involving sine, the fact that it's symmetrical across the y-axis, right, should not be surprising to you, right? The sine is sort of the same over here, right? The sine is the same at pi over 4 as it is at 3 pi over 4, right? That shouldn't be surprising to you that this is the same. That's sort of why I didn't duplicate that first t-chart. Okay, let's now think about why I chose these values. I started at pi, and we see that we go negative here. And again, if we think about why we're going negative, sine can be negative. It goes from -1 to 1, right? On this interval from 0 to 2 pi that we're so concerned about. And when we think about sine being a negative number and the absolute value of b being greater than the absolute value of a, right? That means this term is going to be bigger than this term, and we're going to get a negative number. Previously, we just sort of ended up with a little dimple here. Now we're going to get a negative number, right? So when we think about this graph, okay, we need to think about two more sort of key points. I already used green, so let's use, oh boy, we'll use yellow maybe. Okay, let's think about these two key points. What happens there? Well, r is 0 there. R is 0 there. And we know one of them is at 7 pi over 6. 7 pi over 6. So I know that by the time I get back to this line right here, I better be back at the origin, which is kind of weird. In between pi and 7 pi over 6. So that's in this region right here, this sort of orange region. You'll agree that I'm still positive. R is still positive. So when I plug in, 13 pi over 12 or something scary like that, R is still going to give me a positive number. And if it gives me a positive number, that means it should appear sort of in that quadrant. So I'm going to dip down very slightly in here. Very slightly in here. So it is positive. Probably shouldn't have drawn it that many times. Here, we'll make that a little bit nicer. A little bit nicer. We're going to draw that right in here. I come into this yellow point, right? This yellow point that we highlighted over here. And when we think about what happens now, at 5 pi over 4, I'm going to be at negative 0.4. Negative 0.4. So let's maybe use pink. Negative 0.4. So I'm going to go negative 0.4 in this direction. And if I go negative in that direction, that's really going to be up over here, right? That's really going to be right here-ish. This is this point right here. I'm going to be up here. And we sort of see that we peak here. The most negative I get is at 3 pi over 2 for sine, and that would be up at negative 1. So I used green for those points. Oh, I really shouldn't have used red there. And we'll use green for extrema, I guess. We'll use green for extrema. So that would be negative 1 in the 3 pi over 2 direction, which is actually positive 1 in the pi over 2 direction. So that's up here. So if we think about what this function is actually doing, it's actually going to look something like this. It's going to come up and make this weird shape. Okay, that's this pink piece here. This pink piece here. And then by symmetry, I'm really running out of colors. We'll use this guy. I don't think I've used. I don't even know what to call that. Magenta, maybe? Who knows? By symmetry, we're going to sort of hook back into here. We're going to hook back into here because, again, we have to be symmetrical. Ooh, bad drawing. But we get the idea that it sort of comes around here, right, and looks like that. That's this color here, okay? And then finally, just to complete our curve, maybe we'll use, I don't know. I care way too much about these colors, huh? Maybe we'll use this other blue that we haven't used yet just to complete this other curve, right? We're sort of going to need the opposite of this orange piece where we sort of dip back down and come back up. So that's this guy in here. And we sort of end back at our red point back here at 2 pi. So this is a Limacon with an inner loop. Okay, and I like to look at the graph because it sort of helps me piece things together. It helps me piece things together very slowly. And I'm going to try to do the next one maybe without even a T-chart. You can always rely on them if you need them. They just tend to take some time to actually create. And you can sort of run into some problems on an assessment or something if that's taking too long. So let's try to graph. This is 1 plus 2 sine x. Let's think about graphing 2 plus 3 cosine x. And again, we're all experts with our trig graphs. So we were able to graph this guy sort of right away. And that's great that we remembered that this thing had sort of a peak to valley of 6, right, or its amplitude of 3, and it still had a period of 2 pi, and it's sort of centered around y equals 2, right? So let's think about cosine versus sine, right? We're probably going to be symmetrical about the x-axis instead of the y-axis. And let's maybe get right to it. So when theta is 0, we can see from the graph, right? Again, we can sort of think about this as r equals 2 plus 3 cos theta here, right? When theta is 0, r is all the way out at 5 right away. And I guess we used green for our max and mins. We'll use those again. Okay, so green for our max and mins, and so r is out at 5, so I don't know how I'm going to get to 5 here. Let's say maybe we'll call this 2 now. So this is 2, maybe this is 4, so maybe 5 is here, we'll say. 5 is out here, and then if I wanted to plot my other ones, at pi, it looks like we're at -1 on my graph. And that should make sense, right? If you plug in pi for cosine, here I am making my t-chart in my head. If I plug in pi for cosine, I'll get -3 for that piece, and I'll be at -1. So -1 in the pi direction is really right here. I realize, and as we just graphed this, we forgot arrows on this guy, so I'll add them. We forgot arrows. So again, right, we started here. This was sort of my first point. My starting point was right here, and we went around this way. My bad for forgetting those. Right, we went around and around and around. There we are. Okay, and this was sort of my starting point was this guy right there. Anyway, back to this guy. Sorry for the interruption. So we have these points, and then at 2 pi, we're back again here. So I think a lot of you can sort of think that you could probably just turn this shape on its side, and this is sort of going to be the piece of my inner loop right here, and this is sort of the farthest I am from the origin right here is my outer loop. And you know what, you guys, you're in BC Calc for a reason. You're smart, you're right. But let's sort of think about how we're developing that, and sort of where we are at some key values. So it looks like here, if we look at the graph, again, I like to think about the sort of middle points, right? The middle points where we'd intersect that center, that line at y equals 2. And it looks like, those are at pi over 2 and 3 pi over 2. So let's fill those in. At pi over 2, we're out at 2. That's here. And at 3 pi over 2, we're also out at 2. So that's down here. And I think from now, you guys could be fairly good with connecting the dots if you really wanted to, right? We think about when this thing is getting increasing at its fastest rate, and so on. When it's getting big fast. Right, so we're gonna come down here. We're gonna start we're gonna get smaller slowly, and then we're gonna get smaller faster and faster, faster. I do not know why I just picked black for that color. Let's use this blue. Okay, so we're gonna graph this segment in a blue, right? And so that's gonna start off kind of slow and then get faster, 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 sort of rushing into this guy. So it's gonna look something like this, right? Starting off getting smaller, slow, and then we're gonna sort of rush into this guy where R is getting smaller way faster there. That's pretty good. Okay. And then after that, right, we're still going to be positive. We're still going to be positive in this region here. Still positive in this region here, but getting smaller and going into 0. And where are we at 0 there? We could solve for that if we wanted to, and you might want to do that, right? You could do this on your calculator. We're really solving for where r is 0. So we're looking for the solutions for theta that solve this equation, right? So we want, where does sine theta equal -2/3? And you guys, could find that. It's not like a nice unit circle value, but we see that it's a little before 3 pi over 4. A little before 3 pi over 4. right? That's sort of where we turn to the negative, right? So we're going to want to come in sort of like this, maybe a little rounder like that. And we sort of come into the origin, right? Then again, we have this little loop here. Oops. This little loop where we're going to be negative leading into here, leading into my sort of lowest point on the curve. This little loop where I'm negative, right? We, just to be consistent, right? We used yellow for these on my other graphs, so I'll use yellow for them again. And we have this little loop here where we're negative. And what that's going to look like, again, we would be looking at angles like pi. And instead of going to the left in the pi direction, we're going to have to go to the right because it's negative. And we're going to sort of loop around in here. We're going to loop around. And we're going to come out, again, because all of those angles were negative. And we sort of resume the positive areas at 5 pi over 4. At 5 pi over 4, we're going to resume our positive graphs. And we're going to look like this, right? We're going to resume the positive graph. And we're sort of going to look like this guy here. And then lastly, maybe we use this. We're going to complete our symmetrical curve and sort of come up, right? We're getting big fast over here and then sort of slowly. That is actually fairly good looking, if I do say so myself. So I encourage you to actually play a little bit with Desmos. You can have a lot of fun here. Graphing some things, and you can sort of think about a lot of different things with this new coordinate system that should be fun. We're dealing with this b here, the absolute value b being bigger than a relatively, right? The absolute value being relatively big compared to a. I didn't pick values that were too great, but you guys should be able to think about, if you use Desmos, you should be able to think about what happens if I increase that value. I increase that value from, maybe not 3 here. What if I made that like 10? And the answer is, this inner loop becomes sort of proportionally much larger, right? Proportionally much larger. We can continue to make it bigger, right? What if it's 20? Well, it's bigger still, right? And obviously you can't ever sort of eclipse that, but you guys can play with things. You guys can play with making this negative. Maybe it flips around there. You can play with making this also negative. You can think about whether that does anything. Let's think about one other thing that I thought was interesting, right? It's sort of this notion of, can I move these around? And what way would I move these around, right? If I started with, maybe this guy right here, and I wanted to move this around. Whoa. It's not what I wanted at all. How do I unstretch that? Why did that happen? Anyway, it's very oddly stretched here, and I can't really figure that out. I'll play with that after this, but you can pretend that that's not weirdly stretched out. Oh, there we go. Anyway, while I sort of recenter this guy, there we go. Could I move this, up and down, left and right? Like, is there something that would allow us to do that? And the answer is, not really, right? Can I just take this whole shape and move it way up? Well, theta, given sort of the way we're setting these things up, right? That would be very, very difficult because, we're going to end up with a way to get back to r equals 0, right? If I just have a trig function on the other side, that trig function can probably equal 0 at some point. If b is bigger than a, right? Obviously, with the things that Miss Yam was drawing, right, we don't actually have to have 0 here, right? R doesn't have to be 0 depending on a, but obviously you'll see that if the absolute value of a is less than the absolute value of b, I will have to sort of make it back to 0 at some point. That is the way trig works, right? So that was some Limacons with inner loops. I hope you found that interesting. I'm going to talk to Miss Yam about what problems make sense for you guys to look at. I also forgot arrows on this guy. Bad Mr. Perlis. Bad Mr. Perlis. Right, but we can draw those in really quickly if you remember, right? They go this way. Right? And then the only tricky part, right, is, which way we go on the inner loop. Some people would want to just, I'm on the, the sort of the top side. I want to do the top part of the inner loop before the bottom part. Bad. Okay, so this was just a way of interpreting these things. If you can sort of think about the normal XY graph, you can sometimes easily interpret the polar coordinate graph. All right, so I'm gonna coordinate with Miss Yam for what practice it makes sense for you to do these guys, and I will I'll have a second recording out very shortly about roses. Yay.